Good morning, everyone. I guess everybody's here right now. Um, Welcome to this Mechatronics Lab. This is our week 4, lab 3. Today we're going to continue with Matlab and Simulink tutorials. For today, we're going to focus more on dynamical system response with emphasis on first and second order systems, how to simulate and which are the inputs that are commonly used to evaluate the performance of a first and second order system in mechatronics and control. That's our main goal today. Also, we are going to see some new MATLAB ways to represent the systems. I mean, different from the last week, but also are equally valid if we want to represent dynamical systems, at least from transfer function point of view, as we will see. So for today, this is the lab assignment. It's already on the CAT courses. We are going to watch first the tutorial. We're going to see the tutorial video for this lab, considering all the first and second order system dynamics and some generalities about linear time invariant systems, in order that you can get really quick the idea before performing the lab assignment. Lab is also here. The video is also uploading this link that is in the assignment. So no worries. You can, if you need to access the video, you can access after this lecture anytime that you want. So let's begin. Hello, everyone. Welcome to this second lab on Matlab Simulink for Mechatronics. Today we are going to cover dynamical system response, in this case based on first and second order systems, which are the most common model systems employed in mechatronics. The learning objectives for today are understanding the fundamental response of dynamical systems and principal time domain features using transfer function representation, recognizing stable, unstable, and critically stable behaviors on physical systems, as well as using Matlab Simulink to obtain first and second order system time response in the presence of step and impulse signals. Just to begin, the first type of systems that we are going to analyze during the whole course of mechatronics are linear time invariant systems, or LTI systems. This LTI is the most common representation of dynamical system for mechatronic and controls. It's the most general system that you could use to represent. Why? Because LTI systems are given directly from a ODE, ordinary differential equation, and its input is related directly with its output. It means as much you change your input, your output will have the response in the same magnitude. Some important things about these systems is that you can characterize it using impulse response or natural response of your system in a more straightforward way than any more complex system. Its behavior depends only from current and previous values of the system behavior, and you can, in that sense, predict the future of the system. So this is useful for us in terms of control because we can simulate the performance of our system towards the time goes to infinity. And another really good advantage of using LTI systems is that we can represent it using Laplace transformation. Here we can see an example in block diagram, which will be the most common representation for control systems and mechatronic systems during this course. We can see a system h of t, which has an input u of t and an output y of t. In the time domain, the relationship for the equation that relates the output is given by this formula here. Y of t is equal to ht, which is the model of our system, convolution by its input. In terms of differential equations, this operation is given by the convolution operator, which is basically the application of the system ht times the shift input, in this case x here. That's the convolution operator. This convolution operation is really common for any linear system. However, according to the complexity of the system, this convolution could be really challenging to solve, especially if we have linked multiple Lti systems. Before go more into details of first and second order system, let's continue describing the properties of Lti systems and why we are using the Lti in mechatronics and controls. First of all, the first property is the linearity. For any system ht, which input h1 that produce an output y1 and input x2 that produce an output y2, the linear combination of the input as well as some weights that could have those inputs will produce a linear combination of outputs in this way, as we can see here. For example, the system H that we see before, in terms of a linear combination of x1 and x2 for weights a1 and a2, will be the output a1 y1 plus a2 y2. This is a really good property because we can use superposition and any other linear system and analysis techniques in order to solve the ODE equation and finally solve our problem. Time invariance, it means that the output of the system, yt, is not going to change regarding when the input is applied. It means that if we apply the input xt of h, or we apply the same input x of t after some delay or some sigma time, basically the response of the system is the same. The only difference is that we'll be shifting time by some sigma value. And the other important thing of LTI's property of LTI systems is the causality. It means that the LTI depends only of present and past values to calculate of the input to calculate the output. It means that we don't need future values to represent the system, which is also really useful because we cannot predict the future. So we can using only current and past values, model and analyze our system. Those are some of the three main important properties why we are using LTI systems for mechatronics and controls. Okay, so the LTI models can be represented in two ways. One way is using the time domain representation. The other one is using the frequency domain through the Laplace operator. Why is, in our case, we are going more into frequency domain because once we have more complex systems, it will be easier for us to analyze the interconnection and interactions of our system directly on the frequency domain. If we see in this way, in the time domain, as we said before, we need the convolution operator in order to know the relationship of the output y in terms of the system ht and the input h of t. If we go to a frequency domain, basically we can do the same relationship just by the multiplication of ys of hs times xs. This in the frequency domain. It means that here we have to use convolution, and in frequency domain it means using Laplace transform. We just need a product operation to make any analysis, which is relatively more simple than deal with big convolutions that could be tricky, especially if our system is too complex and has many interactions among each other. In LTI systems itself, we will have two main important signals that we are going to use to evaluate the performance of our system. One of the signals is the unitary step, that is represented by this graph, and its time domain representation is given by this formula, where essentially says that our system, independent of many steps that we could have, this step will be 1 if x belongs to A, in this case A belongs to this side, and 0 if doesn't belong to A. The unitary step for us will represent the sudden change into a system, into the input of a system. For example, could be like if we are driving our car and we push the gas, this step represents the moment that we push the gas. So we goes from one state to another new one for the input, and that sudden change is going to represent the dynamic behavior of our system, how the system behaves jumping from one state to another one, which is its response. That's the main or the most important property of the unitary step input. Is the most common input to evaluate the performance of any control system, which is also really good. And most of our analysis in mechatronics will be based on this input. If we go to the frequency domain representation of the unitary step, the representation is this one here, 1 over S, which is equivalent to the integrator operator. So in frequency domain, we will have this representation for our unitary step. On the other hand, the unit impulse, as you can see here, is just the delta Dirac function, which in this case, as you can see, only we have a small impulse at t equal to 0. That impulse is equal to 1. And this is the time domain representation. Basically, is 0 for all the other times, but here we only have one step. This with difference regarding with the unitary step. The unitary step, once we reach the new state, we keep the other state as t goes to infinity. In this case, the unitary step is just an infinitesimal jump between 0 and 1, and just lasts for one sample. In this case, as you can see here, this is just an impulse. In the frequency domain, this impulse is equal to 1. It means that it's just one impulse, one just a quick event that happened and then disappear. Why is useful the unit impulse response to analyze LTI systems? Because if this allows us to see which is the natural response of our system. It means if we just push the system for once, we excite the system just for one small time, what is going to happen? For example, thinking a brick. You have a brick and you push that brick just for one moment. The brick is going to displace over some surface, and after some time, the brick is going to stop. That's essentially the idea of this unit impulse. You have the brick, the system is your brick, and you gave that input or excitation signal that is just like push the brick just push the brick, and you will see how your system behaves once the impulse energy is removing again and again. On the next step, we are going to see the difference between step response and unit impulse in graphical way, so you can be more comfortable in order to see how is the difference between step and impulse. Remember, those are the most important inputs that we are going to use to analyze any kind of system, so keep that in mind. Remember this frequency domain and time domain representations for step and unit impulse response. Okay, as we see from the previous lab, we are using the transfer function representation to work with LTI systems. The transfer function representation is easier to analyze or understand in the frequency domain. If we see the transfer function is given as the ratio between the output and input of your system. Thus, the input and the output can be represented also by a huge polynomial, as you can see here. The polynomial in the numerator has this b and has this degree m, and in the denominator, the degree is n. So the transfer function can be a huge polynomial in both numerator and denominator. So some important properties of this transfer function is that we can talk about proper and improper transfer function. In theory, every time that we want to work in mechatronics, our transfer functions should be proper. It means that the order of our denominator is always greater on or equal than that our numerator degree. This is important because only proper transfer functions can be implemented for simulation, control, and physical implementations. So the denominator degree always should be bigger than the numerator degree. If we have an improper transfer function, our polynomial degree on the numerator will be always greater than the denominator, and this is not physically realizable. So always we are trying to make our transfer functions proper. Some important features of this transfer function. The denominator, in this case, is known for any transfer function that you want or you have. The characteristic equation. Why is the characteristic equation? Because the denominator defines the dynamic response of your system, of your Lti system. So if you want to see how long takes your system to stabilize, you should check always your denominator. Take that in mind always that you want to analyze any transfer function system. Analyze your denominator to know your transient behavior. Of course, if we are talking about polynomials, indeed we have some roots for the numerator and some roots for the denominator. In the case of the numerator, the roots of this polynomial are called zeros, and the roots of the denominator are called poles. We always are going to look at the poles to analyze the stability and the dynamical response of the system. So keeping these names, poles and zeros, and also keep this as characteristic equation of our transfer function. All right, so let's see an example. We have here this transfer function. We have one first order polynomial on the numerator, second order polynomial on our denominator. This is a proper transfer function, as we can see here. M is greater than n. Our poles, in this case, if we calculate the roots of this polynomial, we can factorize, as we can see here, s plus 1, basically the two roots of the second order polynomial in the denominator are two real repeat roots in -1. We have in this case 1, 0, which is the roots of the numerator. S is equal to -2. The characteristic equation of this system is this one from the denominator, s squared plus 2s plus 1. This is the unitary step response of this system. We are going to see later how to calculate this using Matlab. This is a stable system in the sense that our system response is going to infinity as well as the time goes to infinity. Our response reaches some steady state value here. So we can set now that this is a stable system. Something important that you should consider when you are analyzing transfer functions also is the real and complex plane. Remember that the Laplace operator is related directly with the j omega. It's related to j omega. Therefore, we are using real and complex numbers inside this transfer function. And that j and omega depends on the frequency of the system. So we can plot or make a real and complex plot, as you can see here. Real is always in the x-axis and the complex is in this vertical axis. And we can plot, in this case, the roots of our system. For example, here we can see S1, S plus 1. It means that our two roots are -1. We can plot here. This x represents the pole. This circle represents the 0. In this case, because both roots are the same, both roots are located here. And here we have our roots for our numerator, which are the poles. And the zeros, in this case, we just have 1, 0. It's coming here in -2. This plane is also called root locus, or geometric space of your roots. And this is important in terms of the stability of your system, in order to see if your system has this kind of behavior that reach a steady state value as t goes to infinity. Now in the next slide, we're going to see how we can determine if our system is stable or unstable. Let's define first which is stable, which is critically stable, and which is unstable. This is given by the roots of your system. In this case, the poles of your system. Is the stability of the system is defined in terms of that. Remember the plane that we plot before? Real and complex, real and imaginary axis. Okay, we have to define in the following way the stability of the system. First of all, a stable system. The system output y reach a steady state value as t goes to infinity. It means something similar to this. As t goes to infinity, this value stabilizes, in this case, in 2. And if you go t to infinity, the value should still be 2. Critically stable behavior is something like this, as you can see here. This critically stable behavior, the response of your system becomes oscillatory. It means like a sine wave, a periodic oscillation. It's not unstable, it's not stable, it's just oscillating around one point. So for that reason, it's critically stable. And we have also the unstable behavior, which basically says that if your output wise is going to infinity as the time goes to infinity, something like this. It's going to infinity. It's going to increase forever. We don't want that behavior. We always want that our systems behaves in this stable, with this stable behavior. So based on the roots of the system, it means the poles of the system in particular, we can determine if our system is stable. But how we can do that? We have to check in which region of the real complex plane our poles are located. Let's define in this way. Stable, our system will be stable. It means we'll reach a steady state value if all the poles of the system are in the left half plane. So here in this region, it means that all the poles, these poles here, all of these are negative. That's the main request for stability. All the poles should be here. We are not wondering about the zeros because the zeros has further implications into the performance of the system. But for now, for stability, we just said that our system will be stable if all our poles are in this region. This region is demarked by the imaginary axis. It means that everything to the left of the imaginary axis is stable if the poles are located in this region. Unstable if any, look at this, any of the poles of the system are in the right half plane. It means that we could have 3 poles, 2 in the stable region and 1 in the unstable region, and our system will be unstable just because one of those poles is in this unstable region. The unstable region is everything to the right of the imaginary axis. So if any pole comes here, we are done. Our system is unstable in this case. On the other hand, the system will be critically stable if our poles are over the imaginary axis. It means if we are in the boundary, we will have this oscillatory behavior. So those will be the 3 conditions in this case for stability: stable, unstable, and critically stable. Let's go to see some examples in order that you can understand better graphically what it means about stability with stable, unstable, and critically stable. This is our example from before. The system in this case is stable because the roots of our system, in this case the poles, the denominator roots, are in the left half plane. If you can see here, both of them are minus 1. Therefore, our system is stable and has this response. However, if we made that change the sign here, same system but we just change the sign, our roots now will be located in the right half plane. So our system response will be unstable, as you can see here. You see that the response is going towards infinity as t goes to infinity. So this is an unstable behavior and we don't want that. The idea of control, any type of control that you build in the future during this mechatronic course, will be guarantees that your system is not going to have this behavior. That's something that you don't want. You want behaviors such like this. So keep that in mind always, that you think stable and unstable behaviors. All right, so we have many different types of transfer functions that we could obtain for any dynamical system. However, in terms of talking about controls, we should figure out two types of transfer functions that are the standard for control engineers to model the systems, understand its behaviors, and design controllers. Our case, as many control engineers' case, is the first and second order systems. First order system is given by first order transfer function. Its canonical or standard form is this one here, k over tau s plus 1, similar to last lab RC circuit transfer function. Second order system, this is the shape of this is standard form of the second order system, omega n squared over s squared plus 2z omega n s plus omega n squared. This is the original, this is the standard form. And if we have higher order systems, the higher order systems for n greater or equal of 3, the shape will be, the standard forms will be something like this. If we have more terms, of course, it will be 4, 5, 6, 7, whatever we have increase. This standard form also can be together with a delay time. This delay time is given by the system nature of our dynamics and is represented in the frequency domain by this exponential Euler minus Ls. This L represents the delay time that your dynamical system response will have. In terms of controls, this delay that, as you can see, we can add just simply at any of the standard forms of transfer functions that we see here, could be something really challenging to deal with that, because we have some delay in our system. So the actions that we are executing over the system will take some time to be reflected. So this delay is something really important and is challenging to eliminate, especially in really, really complex systems. Therefore, this is something that we shouldn't take, so we should take with careful. But during the course, we're going to learn some strategies to deal with this delay. In the same way, as you see, we can add to all these standard forms. For our case, in mechatronic course, we are going to focus more on first and second order system. Remember always these standard forms with and without time delay for our first and second order systems. That will be the guideline for our course. Okay, let's start with the first order system. During the last lab, we go through this first order system on the tutorial. Right now, we are going more into the system and its performance properties. The advantage of first order systems is that we can represent flow and thermal systems, which are really commonly employed in industry for any reason: chemical industry, food industry, petrochemical industry. This is the most common process that you could find. All of them are represented by a first order ODE as well as a first order transfer function, as we see here. Is one of the baselines for controller design and implementation. So learn this form give you a lot of sense regarding to any controller design in the future, as we're going to see as the course and the lab goes further. And we can, and according to the values of tau and L, last time we discussed that this is the time constant of our system, this is the gain, and in this case, this L is the amount of delay that we have in our system. This is something that we said before. We can determine if our system is time domain or lag domain. If the time constant tau is greater than the delay, we can say that our system is time dominate system. If our delay is bigger than our time constant, our system is lag dominated. It means that in this case, the system could be challenged harder to control because we have a lot of delay because our control action is in fact reflecting the right control over our system. So take this in consideration every time that you see a first order system: time constant and delay. Here, for example, there is a graph, as you can see, for k equal to 10, time constant equal to 1, and we have two different delays. One is 0, it means no delay, and the other one has a delay of 5 seconds. This L is always in seconds. If you see here, this is the response with 0 delay, the blue one, and with 5 seconds delay, you see that the response begins after 5 seconds. The shape is exactly the same, but our system dynamic is behind the other one. The response is similar, but we have some time shifting, time delay. So this is what we mean about delay in any LTI system or any control system. This is the delay notion itself. Take in consideration that if you are controlling, I don't know, an airplane, this delay could be unacceptable because your airplane needs to correct course or take action in terms of milliseconds. This is a quite long or slow system, like thermal and flow systems, which used to take hours or days sometimes to converge. So this is the difference between having and doesn't having delay. All right, so for this first order system, we have some features or characteristics that we can analyze. For example, first one is time constant. We mentioned that one in the last time before, in the last lab, is when our system, the time that our system needs to reach the 63% of the steady state value. This is the time constant tau. Settling time, by definition, is the time that your system needs to reach the 98% of its final value. In the case of first order system, used to be between 4 and 5 tau. So that's, remember that values always used to take about that time to reach the steady state. The steady state is the value of the system, the response of the system, in theory, when the system goes, the time goes to infinity. Here in the graphs, as you can see, for example, in this case, after 9 seconds, in the other one, 4 seconds, we already reached that steady state response, that in this case corresponds to 10. It's exactly this response here, but we just extend or expand in order to show the properties better. And we have another property that is the rise time. And the rise time is the time that takes the system from going from 10% to 90% of the steady state value. In the first order system, we can measure all these properties really easy. Tau, it depends on the time constant. In this case, tau for us is 1. This is the setting time for the blue curve, as you can see here. 3.91 seconds is about 4 tau. In the other case, as we can see here, because the delay, we start in 5. And here the steady state, the setting time is around 8.91. It means if we add, it's exactly this time here. The main difference is that we have that 5 seconds shifting. Our steady state value for both of them is 10, in this case given by the gain of the first order system. And we can measure the rise time really quickly. If we have here like 10, our final steady state value, we reach 1, here maybe like 0.2 seconds, and we can set that 9, in this case here, could be around like 2.2 seconds. So our rising time between 10 and the other one is around 2 seconds for this system. It means that our system has a good response has this type of properties here. This is in the case of first order system, which is like the basic system that you could find in industry, or any thermal or flow system. Here you can find the code to perform the simulation. As you can see here, it's pretty similar to the code that we made last time. Again, we define the transfer function using the complex operator S and the TF command transfer function. Here we have G and G1. I mean, here I define two different transfer functions. One is without delay, and the other one is with the delay. You can see here that is basically EX, the exponential of -5, that is the delay, time S. This is the transfer function with delay, this is the transfer function without delay. This is one way that we can implement the delay into a transfer function. Here we have some plotting operations. In this case, I'm using the subplot command in order to generate this response. Here, the system, the first order system, is also called first order plus the time, because here we have this delay. Every time we have the delay, we can set first order plus the time system. Here we have the step response of both systems, as we see before. But now also we can introduce the impulse response. But how we calculate the step response and how we calculate impulse response for these systems. In that sense, we made a small change regarding to the last time. As you can see here in this side, we are using the function step. The function step in Matlab basically calculate the unit step response of the system. If you see here, I put G and G1, the both transfer functions. And in this way, if we use a step, the step function, and using this command, we can get this graph here, basically with these both graphs, as you can see. Using this command step, we can get the unit step response of G and G1. If I only want to calculate one response, I just use G, or just one of the transfer functions. But if I have more than two transfer functions, I can just put comma and all the other transfer functions, and we will have multiple curves here. In the case of the impulse response, it's the unit impulse response that we see in the previous slides. You see that we use the command impulse here. G1 works pretty similar to a step function. You can see here we have the impulse response here and here. You see that the impulse response is quite different in this case from the step response. You see that we have like a spike at the beginning, and then our system amplitude start to decay. It's like the brick example. You push the brick, and the brick reach some velocity and then start to deaccelerate until it reaches 0. Same with the impulse response with the delay. We have the delay, and in this case, the system goes down again. If you can observe, the amplitude with the delay is less because that physical phenomenon that we speak before. We have some certain delay before we note the reaction of that force. Therefore, in this case, we see that reduced amplitude as we have delay. This is the Simulink block diagram. Last time we built this diagram without major problems for the previous one. Right now we are introducing two new blocks. One is the delay, and the other one is the discrete impulse. Let's go in this way again. Let's go to Matlab. In Matlab, let's go to Simulink in this case. This is my Simulink file for the lab. This is exactly this diagram. This is the step response. This is the discrete impulse or the unitary impulse. And this is the transport delay. You can find those blocks here if you go to the library. Let's wait just that the library loads. We can come here into the library, go to source. Inside source, we can find multiple sources that we can apply to our systems. Random signals, the step input, that is this one here. The uniform random numbers, sinusoidal wave, signal generator if we want sinusoidal, triangular, or square waves. Ramp input, that is also important for controls. And also we have here the constant that we used before. And here should be the, okay, in this case, the discrete impulse is not here. If we want to find the discrete impulse, we can come here to this, we can come here. Okay, it's not in discrete in this case. We can just set impulse. We can search when we don't know where we find it. You see, we are searching here. Let's wait a little bit. Let's wait a little bit for the searching path. It's finishing. Okay. In this case, we have the discrete impulse. We can just pull and drag here as we made before. If we go for the step input, in this case, we have three configuration parameters. A step time. In this case, the step time correspond. Let me go to the figure here, to the figure of the inputs. In this case, the step time corresponds to the time when we make the jump between this state and this state. So in this case, will be at 0 seconds. The initial value could be whatever you want. In this case, is 0 to replicate this signal. And the final value in this case is 1. However, your initial and final value could be something different. And the step time is the time when you want to perform the jump. 1, 2, 3, 4, 5, whatever. The discrete impulse, by the other way, simply you just have to specify, in this case, something like the sampling time and the samples per frame. In this case, we're going to keep this by default. This discrete impulse, by instance, is a unitary impulse, so we don't have any problem. Will be this signal here, so we don't have such that problem. The other important block is the transport delay. The transport delay, you come to continuous, and we will find different type of delays: variable time delay, variable transport delay, or in this case, transport delay. For all our simulations, we're going to use the transport delay, which basically lag the signal in order to replicate this delay directly inside the Simulink. So we always grab this transport delay. If we double click, we just choose the time delay that we want. In this case, 5 seconds. This is for the first order system. Something that maybe you are curious is why I have this two input scope. This is pretty simple to fix. I'm just going to call a scope in this case to show you. You see this scope has only one input, but you can came here. You see we have one, but we are missing the other one. So if we plug our pointer below, okay, let me make a zoom. If we put our pointer below the arrow, you see that we have this add symbol. We can just click over there and we can add any inputs as we want to our scope. That's the main idea in this case for this simulation. The results are the ones that we show here, are this one here. Those are our results. Either for one or another response, we have the step and we have in this case the impulse responses. So in that sense, this will be the configuration for our first order system simulation. All right, let's continue. All right, for our lab, we have to use the tank level system. This is the model of the tank level. I'm going through this model really quick. This model has an input flow, an output flow, a tank level H. The output flow of this system is given by this expression, R rho G times H. R is the output resistance of this output flow. Rho is the density of the fluid. G is the gravitational acceleration. This flow is assumed laminar in order to keep a linear ODE at the end. If we assume turbulent flow, we will have nonlinear expressions and will be more complex to solve this system because we are dealing now with a nonlinear system. However, continue with this laminar flow. We will have here, by the conservation of mass, this equation that is basically the change on the volume, that is the area times the change on the height, is equal to the difference between input and output flow. The ODE is given by this, making these replacements and applying Laplace transformation. This will be our transfer function in this case, 1 over AS plus rho, R rho G. Finally, now continue. The transfer function is this one. If we put the transfer function on the standard form, k over tau s plus 1, we will have that k is equal to 1 over r rho g tau a over rho g rho rg. This will be our first order transfer function. However, if we analyze here, you see that between the bottom of our tank and the beginning of the outlet for the flow output, we have a small height. Before we can see anything flowing out our tank, we have to wait that the tank reach at least this level here, right? And that will represent some time. So we have a delay before we can see any of our control actions acting over the system. Therefore, we can add the delay here, and that delay is represented by e power of minus L times S. In that sense, we have that our system, the output of our transfer function that relay the height of the system regarding to the input flow of the system is given by the standard first order plus the time equation. So right now we're introducing some physical effects over our transfer function. So in the lab, you have to follow the steps to simulate the system and perform all the specific steps stated on the assignment. All right, so let's go to the second order system. The second order system itself is one of the most useful, especially for mechatronic applications, because it's the most employed to represent motion systems like velocity and position. The standard form for the second order system is this one. In general, the second order systems or mechatronic systems are really fast and the delay is really small, or there's no delay. So this will be our standard form for the system. Um, if we go to the ODE, this is a second order ODE. Is another baseline for controller design and implementation, because we can implement more control desired specifications once we are designing under this second order model. As you can see, we have two parameters that define this system. One is the natural frequency and the other one is the damping coefficient. The damping coefficient will be really important in order to define the behavior of our system. If you ever take any vibration course before, or even if not, we can set the following. Based on the damping coefficient of our system, we can see that if our C or damping coefficient is 0, our system will be undamped, just similar to this figure here. It means that we have like a oscillatory behavior, just like a vibration signal. As you can see here, also we have some roots on the denominator or poles of our system. For this case, the poles of this denominator are two complex conjugate poles. That's the main idea here. Those are the complex conjugate poles that makes this oscillatory behavior. If C is between 0 and 1, we can say that our system is underdamped with two complex conjugate poles again. But in this case, the main difference, we can see here 0.1, 0.5, and 0.9. The system oscillatory response will oscillate until reach a steady state value. As we go close to 1, that oscillation is less. For example, with 0.1 is really huge. This defines some properties. For example, in the first order system, we never saw that we surpassed the steady state value. Here we see some overshoot, or some values that surpass this steady state. So this is called overshoot, and we are going to see how to deal with that overshoot on the next slide, how we can characterize it. If our system is C equal to 1, the system is critically damped. As you can see here, the system doesn't have overshoot. This is something important. And we have some time response, maybe here like 8 seconds. We can say that our system is steady state. If our system C is greater than 1, our system is overdamped. It means that has two real different roots. And because it's overdamped, its sampling time, its setting time will be really low. For example, here you see that this system stabilizes around 15 seconds and here around 8. So as much as we damp our system, the response will be without overshoot, but will take longer time to stabilize. Therefore, take that into account when you are modeling and you want to design a controller. What exactly are your desired specifications? But this will be a matter for Lab 9. For now, we are understanding what is the main important concept of first and second order system dynamics. Some characteristics of this behavior. This is a typical second order system response. We have the setting time, which is exactly the same for the first order system. When we reach the 98% of the final value, which is around here, 8.8 seconds for this graph. The steady state, the value when the system goes to infinity, which is the value that with the output reach. Rising time, this is a new one. Okay, that's the same that we see before, the time that will go between 10 and 90%. This is our rise time, in this case 1.64 seconds for this example in particular. And the overshoot, that is the maximum value that we reach above our desired, our steady state value. This case is like 1.16. This graph is generated with Matlab. We can see now we can see how we can get these features directly from Matlab. This all of these design specific characteristic of second order system has an equation related with that comes directly from this standard form. Notice that these equations only can be applied if our system is in this standard form. If it's not in this standard form, we will obtain different results. So always that you want to work with a second order system, try to put the system into this standard form. So this is the rising time formula, this is the setting time formula, and this is the overshoot formula. All of these are in terms of z and omega n. So some of the most important ones, setting time is 4 over z omega n. This will be our setting time. Our overshoot is the exponential of pz over square root 1 minus z squared. This value is always bounded between 0. Okay. This value will be between 0 and infinity. That's the bound of this value. But in theory, this value will be between 0 and 1. We want that this value, in many cases, at least for mechatronic systems, for example, for position systems, will be 0. So that's something important. And the rising time here, we want that happens faster, and we want to always reduce this overshoot. This is the example for the second order system. This is the spring damper. This is a classical mechanical system. This is the free force diagram, the ODE from the free force diagram here. The acting force, the damping of the damper, and the spring here. If we apply Laplace transform to the free force diagram, is this one here, and we calculate the transfer function is given by this. This step is really important because we need the standard form in order to calculate the correct features of our system. If we check here, we have the transfer function, that is the relationship between the displacement of the spring damper over the input force, 1 over k equal to k over m s squared plus bm s plus km. This is just mathematical manipulation to reach this form. However, it's really important that you always keep in mind that to keep the same form here, this same form, we need to transform our equations, second order systems, something like this. This is our second order system simulation. Pretty much is similar to the previous one, but here I want to introduce another way to define your transfer function. Here we have the mass, the damping coefficient, the elastic constant. We have here last general variables. We are using again the transfer function command. However, here we are using numerator and denominator to define the polynomials, the coefficients that goes with each element of the polynomials in numerator and denominator. If we go behind, this is 1 over m s squared plus bs plus k. Here, numerator is 1, okay, not much problem. Here we have m squared. This will be the first, this is the second order. The first order term, s goes with b, and the remaining one comes with k. So here we are defining numerator and denominator vectors, and using the tf command, we can define our transfer function. It's a little bit different that we used before. In the previous one, we used s equal to tfs. We define the complex operator s. Here we are using polynomial representation, but it's exactly equivalent if you do in both ways. So either way that you want to consider, you can use it. That's like the main idea. Here, this is just like subplot, step and impulse. In this case, this is the step response. You see that it's really oscillatory. In this case, the impulse response goes to 0, but it's again really oscillatory. I want to execute the code in Matlab. Let me go to my Matlab again. Here I should have my This is the code for the second order system, exactly the same code that I showed you before. I just want to run this code. Here we have both responses, the step and impulse response. If you want to get the feature, Matlab can get for you the features of your response if you want. How we can get a response even for impulse or step response? It's easy. Once you get your step response and you use the step command, you came here, set right click, or can you hear me? Okay, that's weird. Let me check the video again. Let me check the video. I don't know why. I mean, this is just like small detail, but this is just the merely end. Let me check the video again. I don't remember why. I don't really know what's happening. Let me check. Okay. Hello, everyone. Response. However, if you see code in Matlab, let me go to my Matlab again. Here I have. This is the code for the second order system, exactly the same code that I showed you before. I just want to pick for you the features of your response if you want. How we can get a response even for impulse or step response? It's easy. Once you get your step response and you use the step command, you came here, set right click over any of the white spaces, go to characteristics, and you choose, for example, setting time. They said 78 seconds. If we want our rising time, we just check 2.54. Steady state value, they set 0.5. And peak response, that is the overshoot. In this case, it's around 70%. It's huge, the peak amplitude. So this is the way that we can get our system features based on the step response. Something similar we can do with the impulse response. With the impulse response, we only have the setting time, how long we take before we go to 0. And here, this is the peak value that we could have. We can do exactly the same for first order system. We just have to right click and see what is it. But the main requisite is that we use the step and impulse functions to get these values here. If we go to the Simulink, in Simulink we cannot get that characteristic responses. However, if you see the simulation, it's pretty much similar to the previous one. Right now we are going to use only the transfer function representation. It's easy to deal with that. For basically most of our next laboratories, we are going to deal with transfer function only. As you can see here, the response is pretty much the same in both cases. So I think this is the end for today. Thank you so much for your attention. If you have any questions, go ahead and please just let me know if you have any further concern. All right, so that's the tutorial video for today. If you have any questions, please um, you can ask me right now or during this time. The assignment is already uploaded into the CAT courses. First part, basically, you have to replicate the same for the same that you see in the video for the first order system and replicate for these different cases and answer these questions here. And for the second order system, you have to build the simulation for the spring damper, uh, perform the different cases and solve the questions here. All right. So any questions for now? No, looks like no for now. So I'll just be here. If you have any question, just use the text box or unmute your mic and ask the question that you need. Okay, I have some questions regarding to the transport delay and how to build the simulation in Simulink. I'm going to make a illustrative example, but I guess should be exactly the same once you do for the first exercise. Okay. First of all, let's go to Simulink. I open a new a new canvas. Sorry. Go to continuous. Take the transfer function block first. This is what we need. I'm going to use this standard transfer function. You can edit according to the problem characteristics. I'm going to source in this case. One of the inputs that we want to use is the step input. The step input is in here in sources. We just drag here and plug over here. I think the most confusing part is the transport delay. No worries about that. Come here to continuous. Here we come to transport to continuous again. Transport delay. Just drag the transport delay block into the canvas. If look the way that I'm putting everything here, this is the transfer function. The input for the transport delay will be the output of the transfer function. Just as a matter of fact, in Simulink, always the input go to the left and the output go to the right. Think in this way always. Input to the left, output to the right. So in this case, the transport delay, you are going to connect to the output of the transfer function, so that you have the first order plus dead time simulation result. Now I'm going to add the scope. I'm just taking the scope like this. I'm going to connect the input for the system. The input for the system will be the step signal, that is this one here. On the delay, no worries about the other stuff here for now. Just add the time delay that you want in this chart. In this case, it's 5 seconds. Okay. You can set up the step. Step time is the time when we change the state. In this case, let's set that the step time is at 0. The initial value is the initial state is 0, and then second step for the second state for the step response is 1. Okay, I'm going to do this. I mean, this is just as an example, just to show you how things are working. Transport delay in this case is 5 seconds. I just plug here the input in order that you can see the input and the output. I mean, the step and also the output with the delay. I double click the scope. I'm going to simulate the system just like it is right now. Okay. You see that we introduced 5-second delay. So from the beginning of the simulation, we have to wait 5 seconds before the system start to working. And in that sense, also, we see here that is a reference, in this case, the step. I'm going to increase the time. Let's set 50 seconds. You see now we see the response. This is 5 seconds. We start the simulate. We start acting with the delay, and then the system is going to stabilize. I answered your question, Juan. All right. I'll be here up to noon. If you have more questions, you can stay logged. But if you have class next to this lab session, you can log out now if you want.
I have a quick question.
Yes.
The questions that we're supposed to answer for the lab, can we just comment them in into the Matlab file, or should we have everything on a separate like Word doc that we convert to PDF?
I mean, my idea is that you put the codes as appendix on your report. I mean, at the end of the report, you put the code as appendix.
Okay, yeah. Okay, I got it.
Okay.
Thank you.
Sure. For the code, you just have to copy directly the code from Matlab into Microsoft Word or Google Docs, and that should keep the format of the text once you copy.
For the Simulink, should we copy the circuit, not the circuit, the thing we create, and also the oscillation that it gives us, both of them? Like just copy and paste the picture?
Just take a screenshot of the block diagram and and put the picture of the oscillations.
Okay, I got it. All right.
Okay.
Thank you.
You're welcome.
That's all I have. Have a nice day.
Okay, have a nice day, you too.